Hello, I'm Mr. McBrien. This is TEJ3M, Turing 3, Decisions. Yesterday we talked about variables, and we talked about using keyboard inputs in our programs. Today I'd like to talk about decision making and some tools that we'll use in decision making called loops. So, a little bit about decisions in programs. Programs rarely really do the same thing in every single situation. Usually they have to make decisions based on inputs or simply based on values for a given variable. Some examples of this. If the user clicks an enter button, then execute. If the user presses the escape key, stop running. If the temperature goes above 40 degrees, then trigger the cooling fan. So these and many other kinds of decisions are typically defined by an if-then-else set of conditions. If this, then this, else this. So we'll need to make comparisons of values typically, and many of us have already had Boolean training. We're going to do it later in this course. It's going to come in handy. If some condition is met, then execute some code and end the expression. So here's an example I threw together. So in my program, we have a variable, a real number, how much money we have in the bank, and we request the user to tell us how much money is in the bank. We get that value from the keyboard, and then we evaluate that amount. So if the amount is more than, it looks like 6 zeros, more than $1 million, then I'm rich. Okay, and really that's all that program does at this point. Simply evaluates the bank balance. Okay, now I'd like you to actually implement a deciding program of your own. So yesterday, your program didn't give the user a choice of whether to do addition. It simply instructed the user to enter the numbers. Let's add the choice in now. So what I'd like you to do is change your calculator program using the concept you've learned. So ask the user to type Y if he or she wants to add, and type N if they don't. And of course run the calculator if they want to play, and don't run it if they don't want to play. So go ahead and do that now. Go ahead and put together your program and pause the video while you get that completed. Alright, so you may have hit a snag when you did this. So I did the same thing along with you. Did you notice anything about your output when the user chooses to play? Well, here's what I got for my output based on what we've learned in this course so far. So my program asked the user if they wanted to add numbers. The user selected yes. They entered 2 and 2, and our program calculated the sum of the numbers, 4. Hey, it did it successfully, very good. The only problem is my sign-off statement to the user when the user was at the end of my code, and so it signed off as if the user had never asked it. I had created a linear program. So my sign-off really should only have come up when the user chose no. Instead it was coming up in both cases. So we can put another if statement in there. But there is an alternative technology that we can use. Because it's such a common problem to have a program want to do one thing if one condition is met, and a different one if that condition is not met, Well, there's actually a system in place to help us do that. We have an else statement that allows us to branch our situation. So if a condition is met, then we execute some code. If that condition is not met, then there's some other code that we'll execute. And then we can end our situation. So now we have two possible choices. And if you notice, they're mutually exclusive. So what's that look like if I implement that in my bank balance program? Well, I can again get the money in the account. If the money in the account is greater than $1 million, I can decide that I'm rich and make the statement to the world that I'm rich. But if my bank balance is less than $1 million, then I can make the decision that I have to go to work tomorrow. Okay, so why don't you try to use some of those concepts now? Complete the logic of your program. Now, some of you have enough skill that you have already fixed the problem with that program. But if you didn't already, make the sign-off trigger when the user opts out, opts not to do the addition. So, are there only two options? No, there are often far more than two options that we need to consider for our decision-making systems. So we can continue using our adder program in order to investigate that capability. So you may have had a situation where at some point you mistyped when you were communicating with your adder program. And if you did something just incorrect, a different number than you intended, no big deal. But if you did something crazy, what you probably saw was the debug window triggering. And that's the equivalent of an exception error that you see sometimes in some programs. Another possible symptom you can see in programs is just a crash. And effectively that's what you saw if the debug window came up. So let's imagine that we want to have three situations with our adder, or with, in fact, any question that we want to ask a user that is a yes-no question. So our three situations could be a yes, a no, or anything else. And in order to deal with that situation, we need a more sophisticated logic. So we can use an else if command. So this allows us to check multiple conditions and select which action to take. And in my program I can have if money in account is greater than $1 million, then put I'm rich. Else if money in the account is less than $12, then I can make the statement to the world that I'm poor. And if I have something between 12 and $1 million, well, at that point, this is all of the other conditions. Notice I don't have less than 12, don't have more than $1 million. Then I must have something between 12 and $1 million, because that's the only conditions left. And so I've got enough money for a movie. Hey, anybody up for a movie? And we can end our statement at that point. Okay, so there's what my code looks like. Really, it's exactly what was on the screen. Alright, so to your adder, you can change your program again and deal with the three situations. The user wants to play, the user doesn't want to play, and the user didn't choose from the options you wanted. For example, in really the most logical problem you could see is if the user typed a small y instead of a large Y and you expected a capital Y. You can't anticipate, though, every possible different approach the user could take. When you don't understand, when your program doesn't see something it can interpret, well, you can just output to the user, I'm sorry, I can't seem to understand what you're trying to say. Now, Is it logical, though, to have the program end at that stage? In the case of garbled communication with the program, maybe the program shouldn't sign off just because the user typed yes instead of typing Y, for example. A better design would be give the user an option to try to communicate again. Now for this, we need one more piece of technology. We need a loop. Okay, so loops are simply repeating operations. And almost every program that you'll see will perform operations over and over again. It sometimes doesn't seem that way because we don't think about what a computer is doing while it's just waiting for input. It's all in the background and we just don't see it. But if a computer program didn't loop, if it wasn't looping and monitoring the keyboard, for example, it'd just do a series of operations and then shut down whether the user wanted it to do so or not. And really, it's much more common for programs to execute something that the user wants to be done and then wait for the next instruction from the user. And this waiting aspect is one of the primary functions of a loop. Okay, so our first loop in our Turing training, we can look at a syntax like this. Simply a statement loop, some code that'll be executed over and over again, and an end loop. And that loop isn't saying stop, that end loop isn't saying stop, it's saying this is the stuff that's inside the loop and everything else is outside that loop. Okay, and so here's my first loop program. My loop program simply puts the word ping onto the screen and loops. Anyone see a problem with this? Well, if you took the time to type that into your into your window and executed it, you'll see that things sitting in a loop just keep going. They'll execute over and over again until a condition's met that makes them stop. And that condition could be execute 10 times, keep going until a variable is exceeded, keep going until a key is pressed, run until 10 p.m., run until a user clicks the exit button, or run until the user enters a specific code. Maybe that's an alarm system, for example. But all good programs have a way to stop. So how do we stop them? Well, there are lots of ways. The easiest one is just put in an exit statement. And we can use something like our comparison tool that we used for our if statements previously. So we can add to our loop an exit when condition. And the question then becomes, how does a condition change while the loop is executing? Well, there's various ways that can occur, all associated with the code that's inside our loop. But there's another way that we can design a loop to end, and that's to make it finite. So this kind of finite loop approach, if we want to look at an easy first loop, it simply counts while it's executing, right? So we can instruct x to increment by 1 unit, and we can put in an exit command at the end of the loop, or just before the end of the loop. And so our code, of course, would normally be inserted in here as well. And so in this case, our command would, or our code would execute 10 times before the loop was exited. That's assuming, of course, that x was equal to 0 when we started. There is an easier way to do this. So for that kind of approach, we can, So So go ahead and use that approach and write a program so that you output the numbers between 1 and 1,000 onto the screen. You can do that pretty simply, I think, just using that loop code that we just used there. So we use our loop code, and all you need to do is add in a output to screen command, and you should be able to, and of course amend that to increment to 1,000. Should be straightforward. Go ahead and do that now. Pause the video and do that now. Okay, so you've learned a useful skill, I think, but there is another way to accomplish the same thing. So we have something called a for loop that combines the iteration step that we had there and the comparison step. So in our case, we can have for counter going from 1 to 1,000, execute our code, end for. And there isn't any need to declare our variable for this type of approach. So a very simple finite loop. Run it 1,000 times and then stop. So go ahead and revise the program you did with the the explicit incrementing of x. Go ahead and revise that program to use the for loop concept instead. It should look something like this. Okay, a couple of notes about for loops that you may not anticipate. You can count down. And so you can decrease the counter if that is convenient, if you need numbers in that way. You can also increment by integers that are not 1. So if you want to increment by 10, you can do that. Okay, so as an activity, try improving your adder. Make it so that it keeps working until the user decides to exit by implementing the functionality inside a loop. So essentially what you want to keep doing is keep asking the user whether they want to keep adding until they decide they want to stop, and then exit the loop. Okay, in summary, today we learned about 2 key ways to enable our programs to make decisions. We have if then, else if, and else that allow the program to do different things depending on situations. And we have loops that allow the program to keep doing things until, well, something else needs to be done, even if something else is just shutting down. Now, you've created a number of different programs today. Please remember to submit your code to Classroom when you're done the activities for today. Thank you, and have a great day.